Hello everyone, in this video we're going to learn about magnetism. Let's start with permanent magnets. Permanent magnets are magnets that naturally occur in the world. They were found many years ago and the first compass was made with them. The source of magnetism and magnetic field is moving charges. In fact, you can kind of deduce that if you look at the base units of electric fields and magnetic fields. The base units for electric fields is kilograms times meters over amperes times seconds cubed. And if we divide this by speed, which is meters over seconds, we actually get the base units for magnetic fields, which is kilogram over amperes times second squared. Magnets have two sides, which are north and south, and the magnetic field vectors go from the north to the south. These are other illustrations that show how the vector lines go. They kind of make an elliptical shape and then go back inside the magnet. And also our Earth has a magnetic field, which is the fundamental reasons why compasses work. There's also these U-shaped permanent magnets. Magnetic fields are shown by the letter B. It's a vector quantity and its units are Teslas. The base units for Teslas, as we've shown before, kilograms over amperes times second squared. Uniform magnetic fields go in one direction, which we'll see in a bit. And if you see dots on a paper, it means that the vector lines are actually coming out of the page in a third dimension. And if you see crosses, that means that the vector lines are going into the page, again, in a 3D world. Now let's look at current carrying wires. We know that the magnetism of a current carrying wire is essentially the sum of the magnetism of the moving charges that comprise the current in the wire. So the moving charges actually create a magnetic field, and these moving charges are actually the current here. If the current is in this direction, in order to find the direction of the electric field, we simply use the right-hand rule, which is shown here. So a wire is simply a cylinder, and if you hold a cylinder and curl it with your fingers give you the position of the magnetic field, which is kind of like this. Now here, we take the current as the positive current or the conventional current. If you're being asked to find the negative current or the real current, you should take the exact opposite of right-hand rule, or you can use the left-hand rule in the same way. And again, we see dots and crosses here, which represent that magnetic fields come out of the page in a 3 dimension and goes back into the page. Also, if you look at the cross-sectional area of a wire, then you can still find the electric field lines positioned by right-hand rule. So here the current is coming at us, so 2 out of the page. And if you point your thumb up, you will see that your fingers are actually going in a counterclockwise way, which is kind of like this, going to the left. But if you point your thumb down, which is like here, then you will see that your fingers are curling around in a clockwise way, which is like this. Magnetic fields are equal to the permittivity of free space, which is the measure of resistance of a material against the formation of a magnetic field. And we usually take it as a constant as the permittivity of free space, which is 4 pi times 10 to the negative 7. Then permittivity over 2 pi times the current times the distance to the point where you want to find the magnitude of the magnetic field. So by looking at this, we can infer that the more the current is, the more the magnetic field is. The farther the point that we want to find in the magnetic field, the less the strength of the magnetic field is. Now let's try to solve this question. The diagrams above show 2 current carrying wires. The wire on the left is in the plane of the page and carries a current in the positive x direction. The wire on the right is perpendicular to the page and carries a current in the positive z direction. Determine the direction of the magnetic field at points C and D. We have 2 situations here and we're going to use right-hand rule for both of them. So let's kind of draw a right hand here. So kind of like, actually this is not a right hand. I mean, it's a terrible drawing, but you can see that this is a thumb and it's pointing at the direction of the current, and these are the fingers that are crawling around, so they will go in this way. So once we're at point C, they're going to go to the out of the page. We can't really show it in 2 dimensions, but they're going to go in the positive z direction. Here we see the cross-sectional area of a wire and the current is coming at us, so out of the page. If you point your thumb up, you will see that your fingers will be curling around in this way. So at point D, the magnetic field is going at the negative x direction. Now let's look at this question. Long straight wire carries a current of 2 amperes. Determine the magnitude of the magnetic field at a point 10 centimeters from the wire. Well, here simply we will use our formula. So the magnetic field strength, E, is equal to permeability of free space over 2 pi times the current over R. Now let's plug in the numbers. So permittivity of free space is 4 pi times 10 to the negative 7th, over 2 pi times the current is 2 amperes and the distance is 10 centimeters, but this is in meters, so we'll just say 0.1 meters. These cancel out and we get 4 times 10 to the negative 6 Teslas as the answer. Now let's take a look at force on current carrying wires. So if we have a wire and it's carrying a current, it's going to create a magnetic field. And also if there's another magnetic field, these magnetic fields are going to interfere and create a force. In order to find the magnitude and the direction of the force, we have some techniques. Well, first of all, in order to find the magnitude, we multiply the current in the wire, the length of the wire, and the sign value of the degree between magnetic fields. So as you can see, the length of the cable, the current that is carrying the magnetic field is going to give us the force. And the degree between two magnetic fields are really important in order to find the direction. So here, if you know about vectors, you might realize this formula. Here, by multiplying the magnetic field and the length and the current, we actually multiply two vectors. So these two vectors, which are the magnetic field of the wire, if we take the cross product of them, it's actually equal to their product with each other and the sign value of the angle between them. In a lot of high school magnetism questions, usually this value is 90 degrees and sine 90 is actually 1, so we don't even take it into account, and we just use the right hand rule. This is a little different than the right hand rule that we have seen before. In this one, you don't curl your fingers, you point them out straight, and once your thumb is in the direction of the current and your fingers at the direction of the magnetic field, you get the force in the direction of your palm. The force created by the interference of two magnetic fields is the main principle of electric motors, which was first created by Michael Faraday and then enhanced by Tesla. Electric motors are so widely used, and nowadays we see more advanced usage of them, such as in cars. So let's take a look at this question. A wire carrying a 20 amps current has a length of 0.1 meter between the poles of a magnet at an angle of 45 degrees as shown. The magnetic field is uniform and has a value of 0.5 Teslas. What is the magnitude and direction of the magnetic force acting on the wire? Well, here we're being asked what the force is going to be, so let's put down the formula. The current is 20 amps, the length of the cable is 0.1 meters, and the magnetic field is 0.5 Teslas, and here we also have sine 45. So let's simplify these. This is basically 1 over 2, and we get 10 from that. This is 0.7, and if you multiply 10 by 0.7, we only get 7 newtons as the force. Now let's try to roughly sketch this in order to find the direction of the force. So this is the direction of the current and this is the direction of the magnetic field. If you use the right hand rule, you will see that the force is going to be in the positive z direction, which is going to be coming out of the page. You can also denote it by a dot. Now let's talk about interacting wires. If two wires have magnetic fields because of the current running inside them, then they interfere with us. The basic rule here is that if the current is in the same direction, they attract each other. If the current is in opposite directions, they repel each other. We have learned about force on cables. Now let's learn about force on moving charges. A force on a moving charge is found by the charge of the charge, the speed of the charge, the magnetic field, and the sign value of the angle between the charge and the magnetic field. Also, the force of the magnetic field and the force of the circular motion is equal. So by equalizing them, we can find some answers. So this is the formula for circular motion. So these cancel out. And in a lot of the situations, the angle between them is 90 degrees. So we're going to take this out as 1. And the result, we get the radius equal to the mass times the velocity over charge times the magnetic field strength. So let's take a look at this example. A charge is getting into a magnetic field with a speed of v, and we use the right hand rule to find the direction of the circular motion. So your thumb has to look at the direction of the velocity, your fingers has to look at the direction of the magnetic field, and then your palm is going to give you the direction of the force. Also, one other thing to know about force on moving charges is that the sign value is really important, because if it's 0, so there is no angle between the vector of the charge and the vector of the magnetic field, then there is no force, because this 0 is going to cancel out everything. And the more perpendicular the charge to the magnetic field is, the higher the force is. And also, as the charge and the magnetic field can't be parallel, and if they are parallel, there is no work. Because in order to do work, the force and direction has to be parallel to each other, which is impossible in the situation of a moving charge in a magnetic field. Let's take a look at this question. A proton enters a magnetic field B that is directed into the page. The proton has a charge, positive q, and a velocity v, which is directed to the right, and enters a magnetic field perpendicularly. describe the resulting path of the proton. Now, let's use the right hand rule to find the direction of the force. This proton is going to make a circular motion. Okay, let's use the right hand rule. So point your thumb at the direction of the V, so at the positive X direction. Your fingers at the direction of the magnetic field, which is into the page, which is in the negative Z direction. And then you will see that your palm is going to be looking at the positive Y direction, which is here. If the force is in that way, and the velocity is in this way, and the charge is going to make a move like this. Now, let's talk about a very important concept called electromagnetic induction. Electromagnetic induction is basically the process of generating electricity, and it's really important because our economy runs on it. This is kind of like the opposite of the electric motor. In a motor, a current-carrying wire passing through a magnetic field receives a force causing it to move. But in the situation of a electromagnetic induction, a force is applied causing a loop of wire or a magnet to move in relation to each other. This process induces a current to flow in the wire loop, and induction occurs when the amount of magnetic field, known as the magnetic flux, experience a change. So if you make a coil by simply using some wires and move your permanent magnet in and out of it, then you will create a change in flux. Same thing happens if you move a wire inside of a permanent magnet, kind of like this here. But what is really a magnetic flux? Magnetic flux is essentially the product of the magnetic field times the surface area. So we know that these vectors happen because of the electromagnetic field, and the bigger the area is, the more vectors it's going to get. You can change the flux by simply moving your surface area, moving in and out of the magnetic field. Or you can change the strength of the magnetic field, which is unlikely. The change in magnetic flux is delta magnetic flux, which is the final magnetic flux minus the initial. Or change in magnetic flux is also equal to the final magnetic field times the area minus the initial magnetic field times the area. You can create a change in flux in many ways. If you hold a wire and a permanent magnet closer, then the change in electromagnetic field increases. Or you can simply spin a circle inside of a electromagnetic field and the area is going to change because this is a circle, not a sphere. Or you can use a rectangular object and move it in and out of a magnetic field. Now here we know that the area of an object, which is a rectangle, is its length times its width. Michael Faraday found that if the flux in a loop or a coil of wire changes, then a current is created and flows through the loop or coil of a wire. He also deduced that the amount of EMF created was inversely proportional to the time. So in order to create an EMF, which is basically a voltage or electric potential, you had to change a create in magnetic flux, which could be done both by changing the magnetic field and the area. And the faster the changes, the more the EMF. So this is basically how electricity is created. Again, if you move a rectangle in and out of an electric field, then the width of the rectangle that is inside the magnetic field, which is the part that is creating the flux, is going to change. This change in flux is going to create an EMF. And if this change is fast, then the EMF is going to be a much higher number. So we know that the change in area of this rectangle is going to be the product of its length and its change in width. This is the part that is inside the electromagnetic field. And this formula is often used as meters over seconds. So this is a formula for speed. So EMF is also equal to magnetic field times the length times the speed of the object that is going in and out of the magnetic field. Induced EMF is merely a voltage or electric potential, but in formulas you just replace voltage by EMF. So instead of V equals IR, you just say EMF equals the current times the resistance, or in the situation of P equals IV, you just use P equals I times the EMF. Now we're not going to detail cover Lenz's law, but you should know that if the magnetic flux is increasing, the current must flow in a manner so that its magnetic field counters the increase. And thanks for watching this video.